We are solving question number 52 of GATE 2016 chemical engineering paper, and the question is a PI controller with integral time constant of 0.1 minute is to be designed to control a process with transfer function Gp is equal to 10 upon s square plus 2s plus 100. Assume the transfer function of the measuring element and the final control element are both unity. The gain of the controller that will constitute the critical condition for the stability of PI feedback control system is dash. So let's just first draw this closed loop feedback control system. So the set point of the system will be YSP. Then we have been provided a PI controller. So we can write the transfer function of the PI controller as GC is equal to K1 plus 1 upon tau y into S, and tau y we have been given as 0.1 minute. Then we will be having the final control element GF, the process transfer function as GC is equal to 10 upon S square plus 2S plus 100, and then we'll be taking the output Y. Again, we'll be measuring it using the measuring element G1 and passing it to the system over here. So the characteristic equation for this system, you can write it as 1 plus multiplication of all these blocks in the open loop, that is 1 plus open loop transfer function is equal to 0. So that will be 1 plus K1 upon tau ys into GF. GF we have been given as 1. GC is 10 upon S square plus 2S plus 100 into GM is 1 is equal to 0. Basically, we got this from this 1 plus GL is equal to 0, and G open loop was GC, GF, GM, and GP is equal to 0. Then we replace the values of this transfer function to get this equation. Now we need to simplify this equation, and then we will be having the equation in that will be a polynomial in terms of S, and then we can use the roots criteria for stability to solve to comment on the stability of the system by comparing the coefficients. So let's just put the value of tau y as 0.1 into over here and simplify this further. So we will be having 1 plus K. So tau y is 0.1, so it will go over here and it will become 0.1 S plus 1 upon 0.1 S upon 10 S square 2S plus 100 is equal to 0. We can simplify this further to write 1 plus Kc into S plus 10 upon 0.1 S cube plus 0.2 S square plus 10S is equal to 0. So this will become 0.1 S cube plus 0.2 S square plus 10S plus S times Kc plus 10 Kc upon denominator S cube plus 0.2 S square plus 10S is equal to 0. That is, the polynomial that we are having is 0.1 S cube plus 0.2 S square plus 10 plus Kc into S plus 10 Kc is equal to 0. This is the polynomial we will be getting, and using the root array, the system will be stable if the values of all these coefficients in the first column is greater than 0. So over here, A0 we are having it as 0.1, A1 we are having it as 0.2, A2 is 10 plus Kc, and A3 is 10 Kc. The rest, this A4, A5 will be 0. And now we can find the values of A1. So A1 is A1, A2 minus A0, A3 upon A1. So let's just find its value. Ten plus Kc upon 0.2. That is 2 plus 0.2 Kc minus, over here we are having 10 Kc. So this will become minus Kc upon 0.2. So this value should be greater than 0. That is 2 plus 0.2 Kc minus Kc should be greater than 0. That is 2 minus 0.8 Kc should be greater than 0. So from here we will be having the value of Kc as less than 2 upon 0.8. The value of Kc should be less than 2.5. So we have this value of A1. Now we need to find the value of A2 so that we can find the value of B1. So A2 will be this, A5 is 0. So this term will become 0 and A1 will get cancelled out and we will be having A4. So A4 is also 0, that is A2 will be 0. So correspondingly, this term will become 0. And over here, we will be getting B1 is equal to A3. Rest of term will be 0. So A3 is 10 Kc. So that will be also greater than 0. That is the only criteria that we are having, is the value of Kc should be less than 2.5.